thank you, Ollie, for the introduction. As Ollie said, I'm not a microscopist. He called me a geophysicist, and I always find that geo is an exaggeration. I don't know that much about geo things. I know some, more than the layperson, but my background is in physics and applied math. I work on imaging problems in general and inverse problems in general. And I have a great interest in materials in general. So you can see here on the list of co-authors, I have Hamid and Ollie. Hamid is one of Ollie's PhD students. André Niemeyer and Susanna Hunks are colleagues at Utrecht who work with rock physics. And Jan Zhao is a very important collaborator here. He is a material scientist, he's not a geoscientist, in Arizona State University. And it's an important collaboration because this work is not just about geo things, but materials in general. Another disclaimer I will make here for you is I'm not an expert in machine learning. I have learned a lot about machine learning in the past few years because I work on inference and inverse problems. And so there are problems where machine learning helps a lot, as we'll see here, two examples of those problems. But I'm not here to tell you that machine learning solves all the problems. I'm just here to show examples of problems where now we can have better solutions because of machine learning has to offer. The other thing that we'll look here is that, of course, machine learning has been used for many things when it comes to microstructures. For example, segmentation is a very difficult task, and it's often now achieved very reliably by machine learning. So we're not going to talk about some of those applications. We're going to talk about actually two specific applications of machine learning. I will also introduce to you a concept as to how to think of materials in a way that you may not be familiar with. So with all that said, this talk is going to be fairly high level. I'm not going to go into a lot of details. So if you have questions or you'd like to talk about the details, feel free to contact me or Ollie separately and we can discuss that more. So for the purpose of this talk, we're always thinking about microstructure images. Okay, now you can choose in your own mind what microstructure image means for you. And it could mean, like on the left-hand side, a 3D CT scan image, for example. It could be a 2D FibSim image, or it could be on the right-hand side, what you see here are histopathology images of breast cancer tissue. So there is a healthy tissue here on the left, and there's a cancerous tissue on the right. What is common to all of our images is that they're very complex. And usually we would like to abstract the complexities of our images in a way that generalizes them, because as experimentalists, I'm sure at some point you encountered the criticism that when you do an analysis on a few samples, because that's all you've got, someone will point the finger and say, oh, but you've only looked at a few samples and it's only been in X and Y conditions. So how does that generalize? So some things that we would like to do with images. Right? So here are three very specific goals. The first is to have what we call explainable representations of realistic geometry and composition. What I mean by explainable is that it is some form of math or numerical model from which we can derive interpretations that mean something to us, but they still abstract the structure. We also want them to be realistic. Now, you may think, well, this is obvious, we might want this, but it turns out that doing this reliably has long been a challenge in material science. So I will talk about this very briefly today. If we have such representations, then what we would like to do is to be able to predict complexity. So we would like to take images such as the ones that you see here on the screen, and we would like to make new samples out of them. If we can abstract them, then maybe we can make a copy or a numerical sample that somehow represents the features that we care about in these images. That's the second problem that we talk about. And the third problem here is to relate these structures or things that we see at some scale, whatever that scale may be, and bear in mind that the techniques we're talking about here can be used from the scale of nanometers to satellite images. Okay, so these are not scale-dependent approaches. So we would like to relate them to physical properties, and I'll talk about more about that when we get there. But this is related, for example, someone asked in the chat, oh, how can we get this microstructure information if we're in their very high pressure and temperature experiments? This is one of the ways, because we often cannot do a CT, for example, at very high pressure and temperatures because of the size of the instruments, but we can, for example, acquire acoustic data. So can we relate the acoustic wave properties to the state of the microstructure? Now, these problems are related, as I hope to convince you in the next 20 minutes. So these are our three goals, and these are the three parts of the talk. So let's start with the first, which is how to describe microstructure. Now, some of you may know about this, so bear with me if you do. Let's say you have a binary microstructure here, two phases. Now, this does not apply only to two phases, but it's easier to understand the concepts when we talk about two-phase materials. In this case, you can see a bunch of non-overlapping spheres being the black phase and then a white phase being the background. You can think of these, if you like, for the sake of just discussion, as pores and a matrix. But they could be whatever you want in terms of phases. If we look at the probability that any one digitally simple point in this image could be either in the black or white phase, choose one of them. This is called the S1 or volume fraction. So very simply, this is like porosity, right? So that's the volume fraction of a phase. Everybody knows this concept. Slightly more complex concept is what's the probability that 2 points at a distance, say R, fit in the same phase? This is called the 2-point correlation function, right? So the important idea of going from a 1-point correlation function, volume fraction, to any number of points is that as soon as you go from one to more points, you're relating the geometry of the medium at distance. When you relate the geometry of the medium at a distance, you begin to describe the complex structures in random materials. Of course, you can generalize this. You can go, well, I want really high order information. I have a very complex material that has orders of correlation at different length scales. So I'd like to accommodate that. And you can generate, in principle, whatever you'd like. You could think, oh, any points I would like to include in this probability story. Well, there's a problem. And the problem is that to numerically evaluate these functions, anything greater than 3 is computationally intractable. There are very important mathematical reasons as to why this is. And it's got to do with the fact that this problem is combinatorial in nature. So there are no shortcuts to this problem if what you want is a true information of an endpoint correlation function. But we can cut corners. So our colleagues at Arizona, for example, proposed another way of measuring high order correlations with the so-called polytope function. So what is a polytope? A polytope is a fixed shape. So if you look in the picture in A, for example, you have these geometric shapes here, and imagine that they're fixed. Their vertices are fixed points in space, and all you move is the center of the shape and the scale of the shape, how far the points are per each one of these shapes. Turns out that numerically, to sample each one of these costs the same as a 2-point correlation function. So you can keep adding them and you get some higher order information, and that will describe more complex properties of the materials. Now, you can do this, but what you have to bear in mind is in order for us to be able to calculate this, we're paying a cost. Okay, so this is limited high order information. And in a minute, we'll see what I mean by limited. At this point, you may be asking yourself, okay, so what? I mean, all of you just said is arbitrary. So let's look at a very specific example related to an application. So imagine we want to study compaction. Okay, so this is important, for example, if you're extracting gas from, say, the Groningen field in the Netherlands, and that causes earthquakes. You have to study compaction. So here we have 2 time-lapse CT images of a compaction experiment conducted by our colleague Susanna Hahn. On the left, you have a pre-compaction state of the microstructure. On the right, you have a post-compaction state. We'll look at 2 parts of this material here in red and in blue, and we're going to calculate a bunch of these curves. Okay, so all you need to know about the curves that you see here is that blue is the 2-point correlation function, and the other curves are curves that are related to higher order information. You don't need to know anything other than that. What's important here is that all these curves converge to the same point at the origin here. Okay, and this point is the volume fraction. And you can see right away if there are changes to volume fraction, there are changes to porosity. This is what we expect in a compaction experiment. Here, the top decreases in porosity, the bottom actually increases in porosity. But what I told you is that these curves actually contain quite a lot of geometric abstracted information from the materials. And it's actually pretty hard to tell just by looking at these curves as they are. So we can transform these curves, so we can take out the information of volume fraction, so we can compare their geometry. And we get these curves that you see here. It doesn't matter how we calculate them at this point, but they only contain geometric information. So on the left, you see the curves pre-compaction. On the right, you see the difference of the curves post-compaction to pre-compaction. and you see some shapes in these curves. Now, right away, there are a few things that we can tell about these curves. So first of all, these orange curve that you see here tells us from the polytopes that anisotropy has decreased. From pre-compaction to top compaction, we can tell exactly by how much and where and at what scales by the numbers on this curve. And this has to do with the fact that this picture here had this massive crack in it. At the bottom, we also have very interesting information. If you remember before, I told you that the porosity had increased in the bottom. But actually, what the curve says is true, porosity has increased, but the average size of a pore has actually decreased. How is that possible? Well, the curves show us that there's a negative bump here at 20 pixels distance. And this means that these curves are telling us that porosity increased by the pores actually being crushed, but the grains rearranging so smaller pores at a distance were formed. So the overall porosity has increased, but the structure of the microstructure has been abstracted and captured by these curves. This is what we mean by quantifiable and interpretable descriptions of a material. What you need to remember from these curves is that, yes, we could have done these analyses, for example, with structure tensors in an image, but a structure tensor would not have abstracted these properties so that they represent not only this sample, but any sample that is statistically equivalent to this sample. These curves do precisely that. So is there a way in which we can explore this very powerful abstraction capability of such statistical microstructure descriptors? This leads us to our next problem. This problem is referred to in material science as the reconstruction problem. And this is the problem where you start with a sample. So take this sample here, this is a segmented version of the Fontainebleau sandstone. Okay? And we have one sample, and let's say we want to generate a numerically equivalent sample to this. The approach is the so-called reconstruction, where we sample statistical descriptors, and from the statistical descriptors, we solve an inverse problem. We solve an optimization problem by asking, give me another sample that matches these statistics. So this produces, for example, in 2D, a structure like this for 2-point correlation functions, and in 3D, it can actually reproduce a structure. And you might think, well, this looks good. I'm happy with this. Now, whether or not you're happy with this may depend on what you want to do with this reconstruction. I would argue that if you wanted to represent fluid flow, this reconstruction is probably not accurate enough for your purposes. If you wanted to represent statistical or static mechanics, for example, so geomechanics, this may be a good enough reconstruction. It depends highly on what you want. But what happens when the material is more complex? So here's a sample that's generated from a laser speckle pattern, and you can see right away that there are multiple scales of correlation. So you have the little black bits that correspond to each other. You have these bigger blobs that have somewhat of a spatial distribution and shape, and you have these line-like structures. So there's at least 3 scales of correlation. If we go through the same process here of solving this optimization problem for a 2-point correlation function, this reconstruction is pretty bad, as you can see. It looks nothing like the sample. And the reason for this is that if you use 2-point correlation functions, reconstruction will fail because you cannot capture such high-order correlations. This is why we described to you that we have to have ways of describing high-order correlation. Well, as it turns out, if we use the polytopes, this would fail also, because if you remember, I said that polytopes have limited information about higher order correlation. In fact, they're so limited that they cannot enable reconstruction either. So is there a way out of this? And this is where machine learning has come in the past few years. So in the past few years, people have asked the questions, can we look at very, very complex material and reconstruct them by the means of machine learning? And people looked at very wide options for machine learning architectures. And the community more or less converged into the fact that generative networks are good options for this problem. So what's a generative network? A generative network is a network that takes in an input and predicts itself. I'll show you in the picture. So that itself is not quite exactly the same version of the input, but it is the same version of the input to some statistical metric, okay, to some measure of difference that is statistic and not bit by bit equivalent. So here's an example of what a generative network looks like. This is an example of what is called a variational autoencoder. You don't have to specifically care about this example, other than when I come back to it later on, I'll explain why we like autoencoders, in particular in our group and with our Arizona colleagues. But the idea is that you have a network, like what you see at the bottom here. Can you see my, oops, can you see my cursor? It's important now.
Not really.
And now?
Yes.
Yes. So you can see a network. This is input to output. And remember, output is a copy of the input to some statistical metric. Now, this network, when in training, will take the input and will pass it through the network. And as it goes through the convolutions in the network, it will compress the number of coefficients that you need to describe this model up until what's called here, in this case, a latent space representation. Think of this as a set of numbers that compresses the information of the sample. And then it decompresses it to make this copy. When you're training, you give a set of images that you say, keep updating all of my numbers in this so that the latent space works exactly like it's supposed to do. In terms of microstructures, the way we do that is we define some sort of metric that minimizes the potential of creating a structure. So it'll start with something that's very random, and it tends to converge over training to something that has the structure or the patterns of the structure that you intended to reconstruct. So how does this work? Does it work well? Well, let's look at an example from our very own Hamid Amidi, one of our PhD students. So here you have two sets of images. Top is a feldspar-rich material, correct, Ollie? I don't know very much about these rocks, and I think bottom is a serpentinite. Is that correct?
Correct.
Yes. So left and right are different versions. So one of them is real, the other one is fake. It's generated by, in this case, a generative adversarial neural network, which is a type of generative neural network, not the same as the autoencoders as I just described. If I asked you to decide which one is real, which one is not, you're probably debating. If you're an expert on these specific types of rocks, you may be able to tell, but if we look at the collection of our images, even Ollie, who's an expert, is pressed to say which one is real, which one is not. So this works really well. And I'll show you. So the ones on the left are reconstructed by machine learning. The ones on the right are actual real samples. Now, after we do the machine learning, we can take some of our metrics, our high order metrics, in this case, those polytopes that I told you about, and we can ask the question, has the machine learning reconstructed samples that carry out the high order statistics, that maintain the high order statistics of the original samples? And what these pictures here show you is that that is true. So for the top, actually, this case, this is a hexagonal polytope, and you can see that it becomes random very quickly. There's not much order in this sample for that high order of correlation, but in this serpentinite it does, and you can see that the reconstructed GAN model and the real one come really close within a 95% confidence interval. This is really exciting because it tells us that a generative neural network is capable of reconstructing high order complex geometries, even though we didn't ask it to do so. This was not part of the metric that we used to train the network. Unfortunately, however, this comes at the cost of explainable descriptors. So the network now describes the properties, the essential abstraction of this material. But if we look at the numbers in the network, we can't make sense of them. Okay? They are not human readable. We cannot interpret them in terms of geometry. We can reconstruct the material, but we let go of the abstraction. So can we paddle back on this? So this comes back now to our autoencoders. So this is our collaboration with our colleagues at ASU. The answer is we think so, but we have to engineer neural networks specific for our problem. How do we do that? Well, we look at a variational autoencoder and we say, well, we want our latent space to mean something. So what we do is we replace the computations, the features that the network uses, the convolutions, to represent those that have geometrical interpretability, i.e. statistical microstructure descriptors. So this means that the latent space representations that we train here, so this compression, are in fact geometrically interpretable, but they're also data-driven, right? And here you see our first examples in 2 dimensions. So you see ceramic composite, you see concrete, and you see sandstone reconstruction. Here you see real samples and reconstructed samples. You can see that there's a bit of work to be done so that these are better, but we're getting there. And what's important here is that we can go into the latent space representation. This is a very, very small subset of what comes out of a network. And we can look at these values, and they're related to actual geometry. So this yellow point here is related to a triangle of correlations that's oriented in a very specific way and has a very specific dimension across the material. So if the number is low, it means the material has no correlations in this shape. You can see the number is high, slightly higher over here, so it has longer correlations with sort of anisotropic direction. This is how we're building networks that have geometrical interpretability. This is only in 2D yet. We're still going to build it into 3D. There's a lot of work to be done. So finally, can we relate this to physical properties? And the important reason as to why we want to do this is that we cannot always have direct access to the microstructure, and we have remote access to physical properties. Example, here is a CO2 sequestration lab experiment by Susanna Hunks. Here you see the microstructure before and after injecting CO2. And what you see here on the right is you see the response of an ultrasonic waveform at different levels of CO2 injection, starting here in 107 ml all the way to a lot more. And you can see right away that the amplitude decreases, which means the sound gets softer. And you can also see that the waveforms get slightly elongated, which means that the sound gets lower pitched. Okay, this is the effect of acoustic attenuation. Now, can we explain this somehow and relate it to the microstructure descriptors? Because if we can, that means that we may be even able to reconstruct, to recreate a fake sample of the microstructure based on something like this, remembering that these structures here are several times smaller than the dominant wavelength. Right? These pictures that you see here are maybe 20 times smaller than the wavelength. So let's go back to our experiment that we had before. We can take these curves. We have the theory. We've studied this problem to take these curves and predict their acoustic properties. Okay, so remember, top is in red, bottom is in blue. So let's look at a prediction of what the acoustic properties would be before and after compaction in our toy experiment here. Well, what you see here are two curves. On the left, you see wave speed, that is the speed of sound. In the right, you see a wave attenuation, the thing that was responsible for the behavior of those waveforms as we put CO2 in the experiment that I showed you before. And you see the curves for top and bottom before and after. If you look on the horizontal axis of these pictures, you see lambda over L. So this is the wavelength divided by a length scale of the material. It starts at 4 times the wavelength, 4 times the scale length being the wavelength, and ends at 20. This means that this is a high frequency, this is a low frequency. And you can see that wave speed doesn't vary very much with frequency. Its magnitude changes because compaction either increases porosity, which is what happens at the bottom. So that's why the velocity decreases at the bottom, and it collapses the pores at the top, which is why the velocity increases at the top. But notice, very importantly, that attenuation has a behavior with frequency. And this behavior maintains information about geometry. And we know this because if you remember observations about porosity, the top before and the bottom after, these two curves that you see here at the top, had similar porosity. But the geometry of the pores, if you remember my description of what we got from those curves, was very different. And because the geometry is different, these curves start the same, but they become different here because the geometry of the pores is different. So wave speed and attenuation depend on both the contrast of the properties of the material in the volume fraction, in this case porosity, but attenuation carries information about geometry. So can we use this? The answer is yes. Let's look at an example here of a different type of machine learning application. So what we did here is we took random forests, and there's a very important reason why we chose random forests as opposed to a convolutional neural network for this. Feel free to ask if you'd like later on. But the main reason here is that we want a regression problem that is fully probabilistic. That's difficult to achieve with neural networks. Not impossible, but difficult. So what happens is we take some inputs, we bag them into subsets. for many models, which I'll show you in a minute. And then for each one of those bags, we go through a decision parameter split here, which splits parameters for our output. And as we split these parameters, we end up with single samples of our inputs that relate to the choice of parameters that follow through this tree. So we can map what the values of the output are for each input. When you have many of these trees, you can construct a Bayesian inference procedure that allows you to predict the output from the input. The way we do this for our problem is that we start with many 2-point correlation functions, for example, and here you see two types. So you see these are Debye materials that you see here, and these are much more complex materials. We mix them, we predict their elastic properties, we feed them to these networks, and we train them for to create these random forests. And from the random forests, this is the only equation I have for you. This is just Bayes' theorem. We can then create a prior here that we can give any data to and predict the posterior. That is an inference problem. So let me show you what this does. So we can take, so you have different materials. The actual property of the material is in orange. The estimated property only from acoustics, this means only from sound waves, from P waves, is the predictions in blue. And you can see that they come close here. So here you have the Ketton limestone, you have the Berea sandstone, and here you have impenetrable bead packs. And you can see that the estimates are fairly decent for these two, not so much for the first. If we take the full elastic wave mode, which means both P and shear waves in this case, we go to a much better prediction of the 2-point correlation function in this case. Now, if you go back and think about our reconstruction problem, this means that if we could solve the reconstruction problem from this, we could take long wavelength elastic waves and predict a version of the sample that corresponds to the microstructure descriptors. This is the direction where we're going. So this means that we can estimate sub-wavelength geometry from long wavelength data. And this is key to uncertainty on nonlinearity. This is why we need machine learning for this problem. Okay, so let's just recap. We talked about three things today. We talked about descriptions of microstructures. Okay, so we want to be able to abstract them in ways that are quantitative so that we can measure changes, for example, but we can also interpret them, preferably in terms of geometry, but it could be in terms of other parameters depending on your problem. The reconstruction problem is key for this, and the reconstruction problem for decades has been struck with the problem of high order correlations, and machine learning, generative networks in particular, led to breakthroughs in representing complexity, as I showed you through Harmed's work. There are still many challenges. Dealing with 3D structures is still difficult, and that's because of the computational nature of neural networks. We are specifically keen on looking at the 2D to 3D problem. So taking a 2D picture and trying to estimate a 3D structure from a 2D picture, very difficult problem. Multi-phase materials, I mean, I showed you only 2-phase examples, but multi-phase materials are very much part of the research in the community, and generating interpretable predictions of materials is key, and this is a focus for us and our colleagues in Arizona. I also showed you that if you cannot have access directly to the microstructure, you may have indirect access because the effective properties or physical properties are tied to the patterns of the geometry. And I showed an example of using random forest to do a nonlinear inference that is fully Bayesian to estimate microstructure descriptors. That's it. Thank you for your time, and let us know if you have questions.